Hello, I'm Kiran Kedlaya at UC San Diego. My co-authors are Edgar Costa and David Roe, both at MIT. Our paper is entitled Hypergeometric L-functions in average polynomial time. The purpose of this talk is to unpack the title of the paper, give you an idea about the statement of the main theorem, and briefly indicate some of the ingredients that go into the argument. At the end, I'll present a table of contents of the paper and indicate how those ingredients line up with the contents of the paper. More discussion about details will be held in the live session and on Zulip. Let's begin. Let me start by unpacking the term L-functions. So by way of recollection, let me remind that there is a notion of an arithmetic L-function associated to a smooth proper scheme over a number field. There's actually a family of such things for any given x. These are certain Dirichlet series defined by Euler products indexed by finite places of k at which x has good reduction. So let me specialize that to the simplest case where x is spec k itself. Then this becomes a very familiar construction of the Dedekind zeta function associated to a number field. This is defined as a product over prime ideals. And for each prime ideal, you get a very simple Euler factor, which in the case k equals q reproduces the Riemann zeta function. Another familiar example comes from elliptic curves. In the conjecture of Bergin-Twinnerton-Dyer, one finds an L function of the following form. You take a product, now you take only the primes at which x has good reduction, and you take this degree 2 polynomial in the norm to the minus s. And the coefficient AP is the trace of Frobenius of the mod p reduction of x, which is closely related to the number of rational points on the mod p reduction. In general, this family of L functions is indexed by a parameter that ranges from 0 to twice the dimension of x. And the factor corresponding to a prime ideal p is extracted from the zeta function of the reduction mod p via this factorization coming from the Weil conjectures. On the previous slide, the example of x equals spec k was the case I equals 0. The example of x in elliptic curve was the case I equals 1. In general, it's expected and known in a few cases, like for the Dedekind zeta functions, that these L functions have analytic continuation and functional equation to the entire complex plane after suitably completing the product with one factor for each finite or infinite place of k. The factors at infinite places involve the classical gamma function. And once you've done that, you then have access to a rich theory of special values of arithmetic L functions. I mentioned the Bergin-Twinnerton-Dyer conjecture, which in turn is loosely inspired by the Dirichlet class number formula. In the other direction, you can generalize to conjectures of Bloch and Kato, Deligne, Beilinson, and so on. In general, a single L function can arise in various ways. For example, if you take two elliptic curves, or more generally, two abelian varieties, if they are isogynous to each other, they have the same L function. And the converse is true by the Tate-Faltix theorem. In general, there are other ways to construct arithmetic L functions that do not specify a particular geometric origin. A familiar example, if you take a weight 2 rational eigenform for the group gamma naught n, you get an L function from that, which does match some elliptic curve of Q by the Eichler-Shimura construction, but by the previous comment, that elliptic curve is only well-defined up to isogeny. So really, it's a matching between a single modular form and an isogeny class of elliptic curves. And no one of those curves is distinguished unless you choose some mechanism to break the tie. So a primary goal of the LMFDB project, the L-functions and modular forms database, is to tabulate arithmetic L functions with diverse discrete parameters, such as the degree, the weight, and the Hodge numbers. This paper is part of a project to add hypergeometric L functions. As their name suggests, they are somewhat related to hypergeometric differential equations, although we won't go into that. These hypergeometric L functions provide examples of L functions with quite assorted parameters. And you can already find some of these on the LMFDB beta site. Let's now consider the combinatorial data that define hypergeometric L functions. A hypergeometric datum of degree R consists of two disjoint tuples, alpha and beta, valued in the rational numbers normalized to lie in the interval from 0 inclusive to 1 exclusive. And each of these tuples is required to be balanced, meaning that the multiplicity of any reduced fraction depends only on its denominator. For instance, if you consider this concrete example, which we will consider later, 1/4 and 3/4 appear to the same multiplicity on the left-hand side, and 1/3 and 2/3 appear to the same multiplicity on the right-hand side. Given such combinatorial information, we can then define a family of arithmetic L-functions of degree R, the length of the tuples, and the parameter is allowed to range over all rational numbers excluding 0 and 1. There will be certain primes of bad reduction that do not depend on Z. These are called wild primes. These are primes at which the alpha and beta parameters are not all p-adically integral. In this example, 2 and 3 are the wild primes. And then there are some additional primes of bad reduction that depend on Z. These are the primes where either Z or Z minus 1 is not a p-adic unit. The L function that you get associated to these data can be interpreted in terms of a specific scheme. However, there are multiple mechanisms for doing this, so there's not a distinguished choice of this scheme. In order to add an L function to the LMFDB, we need quite a few coefficients of the Dirichlet series, typically something like 2 to the 24th coefficients, although the exact cutoff depends on the conductor of the L function. Since these L functions have Euler product factorizations, we only need the prime power coefficients, and the others can then be recovered by unique factorization. And the prime power coefficients coming from the powers of a single prime p all come from the factor in the product associated to that prime p. That factor can be interpreted as the reverse characteristic polynomial of a certain matrix. And so it's equivalent to compute the traces of suitable powers of that matrix. So if you need 3 prime powers for a single prime, you need 3 traces of powers of this matrix. Typically, when one computes L functions, one uses some sort of cohomological interpretation. For example, Scope's algorithm for elliptic curves uses the interpretation of Frobenius acting on torsion points of the elliptic curve. This is essentially a computation in a Tal cohomology. Other algorithms of the sort that I and others have considered involve use of p-adic cohomology theories. In this case, however, we are not using a cohomological interpretation of the Euler factor. We're using a direct trace formula based on finite hypergeometric sums, which have been considered in various forms by Green, Katz, McCarthy, and Bokers, Cohen, Mellett. So this trace formula that you get from these considerations involves Gauss sums. You can then translate it using the Gross-Koblenz formula into a p-adic formula, as was done by Cohen and Rodriguez-Villegas. And just to show you what the formula looks like without unpacking it entirely, I've put it on this slide. The key feature to take away for the rest of these slides is the fact that there's a sum over q minus 1 terms. The other factors are some sort of combinatorial factors that appear here. These only depend on alpha and beta. There's this thing that is something like a product of Pochhammer symbols. This again looks like factorial ratios, except its computation involves the Morita p-adic gamma function. This is the contribution from the Gross-Koblenz formula. And this is a certain p minus first root of unity. There's a unique p minus first root of unity whose reduction mod p coincides with that of z. So this is the only dependence on z. We will discuss the formula in more detail in the live session, but again, the key point to take away for the moment is that it's a sum over q minus 1 terms, where q is the power of the prime in question. This trace formula is implemented in Magma and Sage, so you can actually do computations with it already. For each prime power q, its complexity is dictated by that sum over q minus 1 terms. So the complexity is O of q with relatively small constants. This means that computing all Dirichlet coefficients up to x incurs a complexity of O of x squared up to logarithmic factors. We will ignore log factors in these slides. They are discussed in more detail in the paper. Of course, the case f equals 1 dominates. If you look at the prime coefficients, there are x of those, O of x of those, up to log factors. And so each of those takes complexity O of x to compute. The remaining cases are dominated by f equals 2. There are x to the 1/2 many terms of that form. And again, each of them takes O of x complexity compute. So the total complexity in that case is O of x to the 3/2. So really, the dominant portion of this computation is the prime coefficients. However, the shape of the formula makes it feasible to amortize the complexity over different values of q. And this is the main point of the paper, is that at least in a restricted setting, we would like to achieve a complexity for each trace, which is polylog in x. This is the sense in which we mean average polynomial time. We don't do this at the level of generality that the formula was stated. We make two simplifying assumptions, which I'll discuss at the end. One is that we only consider the prime traces. We only consider f equals 1. And furthermore, we only consider the reduction of the formula modulo p. If you make both of those assumptions, you get the main result of our paper, which is that we exhibit an algorithm to compute the prime Frobenius trace mod p for all primes up to some cutoff x with a complexity that is linear in x modulo logarithmic factors. And we have implemented this in Sage with some optimization in Python, plus an interface to some C code written by Drew Sutherland that does a computation of what are called remainder forests, which I'll come back to. And using this, you can see quite clearly the difference between quadratic complexity and linear complexity if you look at timings, as I've done on this slide. In this slide, we consider the same example that I treated earlier. I pick a specific value of z, 1/5. This turns out to be an L function of weight 1. So it's actually the same to compute this prime Frobenius trace mod p as to compute it exactly. And in fact, the algorithms in Sage and Magma will compute this only mod p because that is sufficient. The first thing you can look at in this table is the Sage and Magma columns, which we've plotted on this log-log graph here. And you can quite clearly see that we're observing quadratic complexity. The slope of this line in the log-log plot is very close to 2. On the other hand, the new algorithm at 2 to the 17th is outperforming Sage and Magma already by 3 orders of magnitude. And if we carry this algorithm out somewhat further, we can get past 2 to the 24th. And you see that the complexity does indeed appear to be linear. The slope on this line in the log-log graph does appear to be 1. The key to this amortization is to reduce the problem of computing this trace to certain subproblems of the following form. Given a square matrix M, whose coefficients are polynomials in a single variable over the integers, and some function of p, compute products of this form, take M, evaluate it successively at 0, 1, up to k of p minus 1, take this reduction modulo p, and do this for all primes p in some range. Typically, we also restrict to some arithmetic progression. You'll notice that there's a lot of redundancy between these different computations because as you vary p, the initial segments of these products are all the same. And so this suggests the possibility of amortizing the computation. This can be done using what are called remainder trees or remainder forests. This computation is very much inspired by the fast Fourier transform. I don't want to talk about it in detail here because Drew Sutherland's talk will also cover this topic in somewhat greater detail. So you can see some details about how remainder trees and forests are set up in Sutherland's talk and also in his paper. Let me just say here that in our situation, the matrix M is relatively simple. It's a 2x2 triangular matrix whose diagonal entries are being used to capture the factorial-like products, the Pochhammer symbols appearing in the formula. And the off diagonal is being used to capture the summation over parameters. So because this is a 2x2 matrix, this ends up being quite an efficient use of the remainder tree technique. The mod p restriction here is not absolutely essential. You can imagine examples where you do this computation modulo p squared. For example, Costa, Harvey, and Gerbich did a search for Wilson primes by computing products of 1x1 matrices modulo p squared. There is some work that may be required to massage our computation to get rid of the mod p restriction. If one did this in general, it would simplify the problem of computing Dirichlet coefficients up to x. It would reduce the complexity from quadratic to x to the 3 halves. The restriction of prime Frobenius traces is somewhat subtler. If you wanted to get this down to x to the 1, you would also have to deal with prime power Frobenius traces. This issue is a little more complicated, and I won't say anything about it here. We will give more details about these points in the live session. I also invite you to engage on Zulip if you have questions between now and the live session. To conclude, let me illustrate the table of contents of the paper. So the paper starts with an introduction with a lot of historical references. It continues with a section about background on the p-adic gamma function, which I mentioned earlier, hypergeometric L-functions and the putative motives associated to them, the trace formula that I discussed, and the complexity considerations that we've seen. Section 3 is a presentation of the remainder tree method. Section 4 consists of some technical lemmas, which are used in section 5. Section 5 begins with a conceptual overview of the algorithm, which I recommend reading before trying to read the details. It continues with the construction of the matrix product, a detailed description of the algorithm, notes on the implementation that I illustrated earlier, and a worked example that you can follow with your bare hands. Finally, section 6 discusses future goals and challenges, in particular, the question of eliminating the restriction to working modulo p and the restriction of working with prime Frobenius traces. This concludes my talk. Thank you for your attention. I look forward to interacting with you on Zulip or in the live session.